The next thing I'd like to talk about are called position vectors. So this is still section 12.1, but this will be a second part to 12.1. So position vectors are vectors giving the position of a point relative to a fixed origin that we'll just call O. So our origin will represent as O. The point P with coordinates -5, 12 has a position vector. So this OP is representing a position vector, which is -5, 12 in column form, or -5i plus 12j in unit vector form. So the negative means we went 5 left, and then we went 12 up. All right, so -5 and 12 up. So the point P with coordinates xy has a position vector. Position vector, again, represented with that origin O. So O to some point P, we can represent in column form, or we can represent in unit vector form. Resultant vectors. So this is something now we'll start to be able to represent different vectors, what happens when we move from one vector to another. This would be the resultant vector. So consider the points of point A is at 2, 3, point B is at 6, 6. So the diagram shows those position vectors of AB and or A and B. We can see that the vector AB is going to be 4, 3, because if we went from here over to B, we went horizontally 4 and up 3. We can also see that to move from A to B, we could describe this movement as either going directly from A to B or first going in an alternate route. So the idea here, instead of going directly from A to B, I went from A back to the origin, and then from the origin up to B. So I could go directly from A to B, or I could go from A back to the origin, from the origin to B. Okay, therefore we could write, well, our vector AB is the same thing as going from A to O plus O to B. The vector AB is called the resultant vector of our vectors AO and OB. And now recall, we can also write AO as a negative of OA. So if we went in the other direction, we'd just write it as negative OA. Therefore, so this is important, AB can be represented as OB minus OA. So to find the resultant vector AB between 2 points A and B, we can subtract the position vector of A from the position vector of B. So this is a formula that we will use. So understanding that there's alternate routes we can take to get between 2 points when we reference our initial vector and represented with the origin. All right, so let's do an example. Suppose points A and B have these coordinates. So now we're working in 3 dimensions. Find the vector AD. So when we are working in 3 dimensions, you can eliminate using a coordinate plane. So don't worry about trying to go in a coordinate plane. Draw what this shape would look like. So we have some origin O. So we're starting out with some origin O. And then A is -3, 2, 0. B is -4, 7, 5. So these are essentially arbitrary points out in space. So eliminate the idea of working off a coordinate plane once we go into 3 dimensions. Okay, so if we're working with this, -3, 2, 0 is our A. B is at -4, 7, 5. These are just points we put out there and we draw this quick diagram. Again, we want to find this vector AB. And order is important. It's going from A, B. So we can use this idea of referencing our origin. Our OA, to get from O to A, is -3, 2, 0. Get from O to B is -4, 7, 5. So those are our position vectors referencing our origin O. Using our formula from the last slide, we know that AB is OB minus OA. So essentially we were going from A and taking the long route. We're going this direction back to the origin and then here. So OB minus OA. When we are subtracting vectors in column form or in unit vector form, all we do is look at the common pieces. So -4 subtract a -3 is the same thing as -4 plus 3 to get -1. 7 minus 2 is 5. 5 minus 0 is 5. All we do is do our operation with like components. All right, another example. Show that points A, B, and C with position vectors, so they're given us in unit vector form, respectively are collinear, meaning that they're all in a line. So we want to be able to show this. Let's just represent our unit vectors in column form. So we know that A is really 1, -2, 3. We know our vector B is -2, 3, -1. And our vector C is 4, -7, 7. We know that AB is going to be OB minus OA. So OB is going to be our vector B because that's based off the origin. So this is -2, 3, -1 minus OA. So 1, -2, 3. When I subtract these, I end up with -3, 5, 4. I'm sorry, -4 by subtracting like components. So -2 minus 1 is -3. 3 minus a -2 gets us 5. -1 minus 3 ends up being a -4. Well, let's also look at what AC is. AC will be OC minus OA. OC, the position vector, is 4, -7, 7. Subtracting 1, -2, 3. If I subtract these, I end up with 3, -5, 4. Now I can see if I were to compare these, I know this was my AB. This is my AC. Comparing the two, I can say, well, AB is really just the negative of AC. Now, because the only difference is this negative, really this is a -1. These are scalar multiples. Therefore, they are parallel. So parallel because scalar multiple. And since they both contain the point A, if they both contain the point A and they are parallel, then they have to be collinear. Okay, so the only way if they both contain point A and they're parallel vectors, they have to be in a line. So take a look at these few homework problems, dealing with now position vectors, resultant vectors, the idea of collinear. Email me if you have any questions. We're going to have one more section for chapter 12, and then that will be the last section in 12.1 to get going, or I'm sorry, one more video for 12.1 because there's a lot in that first section.